Welcome to Lecture 2.1, all about imaginary numbers and complex numbers. Let me see, I'm trying to get closed captioning working here. And I don't know that I'm doing this right, but maybe it says none. Okay, so anyway, I'll go ahead and get started. Hopefully everybody saw the message on the news feed about the midterm. If not, you need to go check the news feed and make sure that you read it carefully and take that chance to give a second try on your midterm if you'd like. All right, I'm going to go ahead and get moving into the 2.1 material. And we see here that 2.1 is all about complex numbers. So let's just consider this following equation here to begin with. We have the equation x squared equals -1. So this says, what can I multiply by itself to give me -1? And if you think about it, -1 times -1, which is multiplying something by itself or squaring something, is +1. And +1 times +1 is also 1. So we run into the dilemma of what could we multiply by itself to make -1, and that's where the imaginary unit I comes in. If I go to solve this equation, I take the square root of both sides, and when I take the square root of something squared, I have x equals the square root of -1, and we actually get the positive and the negative square root of -1 there. Because it's the equation. And we define the square root of -1 as I, the imaginary unit I. So the square root of -1 is I. Therefore, if we have I squared, and we'll talk more about this in just a minute, we would have the square root of -1 times the square root of -1, which is the square root of -1 squared. When you square a square root, they undo each other. They are inverse operations, and we're just left with -1. So the example here of using I to simplify the square root is we have to go back to our product rule for roots, which says the square root of a product with distinct factors, so two different factors. These are not distinct factors. Those are the same factors, so it follows a different rule here. But the square root, or the nth root even, of the nth root of a product with distinct factors is the same thing as the nth root of one factor times the nth root of another. And you could have as many factors there as you wanted. In this case, we have 2 for the rule. So my piece of advice to you is when you're simplifying square roots of negative numbers, always pull the -1 off. Here's what I mean. If I go to simplify the square root of -25, well, think about it. -5 times -5 is +25. +5 times +5 is also +25. So we have to deal with the negative underneath. This is what I mean when I say pull it off. Turn this into the square root of -1 times the square root of 25. We now have a definition of the square root of -1, and that is I. The square root of 25 is 5. So we say that the square root of -25 is 5i. All right, moving forward. The imaginary unit makes up part of what we call complex numbers. A complex number is in the form of a plus bi. The a is the real part, so the real number part, and then we have the imaginary unit, which is the second part. Now, to write a number in complex form, it has to be real plus imaginary, or real minus imaginary. So you can see this little chart breaks down what I just said there. If you are working in my math lab and you are answering with a complex number, you've got to write it in standard form. Unless it's just one term, like 2i right here, you wouldn't have to write 0 plus 2i. Hey Dave, good to see you. I have just started a minute ago on imaginary numbers here, and I've got my video off because I'm at home this afternoon. All right, so when you write a complex number in standard form, you always put the real part of it first, and then plus or minus the imaginary unit part. And like I said, if it's just a single term, like there's just an imaginary part or there's just a real part, unless you're specifically asked by my math lab to write it in standard complex form, then you just write 2i or you just write 3. If you were asked to write it in the complex form, you would need to expand it out and show both the real and the imaginary pieces. Real comes first, imaginary piece comes second. So moving forward, we have 4 values here that we want to write in standard form for the complex number. So this first one, I'm sorry, these are so fuzzy. I was taking screenshots to throw them onto this PowerPoint. So the first number we have here is 6i. If I wanted to expand that into standard form, I have real plus imaginary, or I could write it real minus imaginary, depending on if that imaginary term is positive or negative. So if I wanted to expand 6i into its standard form, it would be 0 plus 6i, real plus imaginary. If I wanted to expand 7 into its complex standard form, it would be 7 plus 0 i's, because I have no imaginary units there. Now, C, this is where it starts getting tricky. And goodness, it'd be nice if I could tell what that said. I think this says 3 plus I over 7. This is where students get super frustrated when they're trying to put it into my math lab, so pay attention here. It has to split up into real and imaginary terms. And what you're looking at here were basically 2 fractions that happen to have a common denominator. So you've got one of them here and one of them here. So to split this up, that's the first thing you're going to do is give each term its own denominator. So 3/7 plus I over 7. We're still not done yet because it has to be real plus coefficient and then the imaginary unit there. There is an understood 1 being multiplied with that I in the numerator of the second term. So I can pull that fraction off since the variable, in this case I, since the variable is in the numerator, I can pull that fraction off and rewrite this complex number as 3/7 plus 1/7 I. Now it's in the form of A plus BI, real plus coefficient imaginary unit. Dave, did that just make sense to you? I believe. Okay. You did come in after I had explained what I was, so hopefully you'll catch on here in a minute. And actually this last problem will help you understand what I is. I'll just put up here at the top, I is defined as the square root of -1. So with this last one, B is the typical way you might see the solution to a quadratic given. And you've got to figure out how to get it into the right form, this complex standard form here. So the first thing I'm going to do is simplify the square root of -9. I can't leave it that way. So I'll just rewrite this so it's easier seen. 2 plus 3 times the square root of -9 over 6. Okay. So the first thing I want to do, like I said earlier, is pull off that negative, give it its own house. And then I have the square root of 9 all over 6. Well, we just talked about the fact that the square root of -1 is I. The square root of 9 is 3. Now, when you're dealing with roots, all of this is multiplied once it comes out from underneath the root. And if you need refreshers on roots, there is a prerequisite chapter of your book that's all on radicals. So if you need that refresher, make sure you go back, watch those videos, go through some of those problems to get refreshed on how to work with roots. So here's where I am so far with getting this thing in the standard form. 2 plus. Well, I have 3 times I times 3, which gives me 9I over 6. And now I'm to the same point that I was here. I'm ready to start splitting into real plus coefficient imaginary. So I have 2, I have 2/6. So 2/6 plus 9/6 I, and these are both fractions that can be reduced, so I've got to, and I end up with 1/3 plus 3/2 I, real plus coefficient imaginary. It must be in that form if it asks for complex form in my math lab. You can do all of this beautiful work and feel like you're done when you get right here, and you're going to go and you're going to put it in to my math lab, and it's going to tell you it's wrong because it wants it in the standard complex form. I saw your comment down there, Dave. Yes, I'm one of those nerds that thinks mathematics is beautiful. All right, moving forward. Is everything cool with that, Dave? Green check, red X, green check, very good. All right, the cycle of I. Okay, so this actually is really cool. And just to clarify, that says the cycle of I. This is one of the things that just fascinates me about mathematics. So we start out with the definition of I. The square root of -1, we just call that I. And then I want to show you a pattern that emerges with I. If we have I squared is the same thing as the square root of -1 times the square root of -1, which is the square root of -1 squared. When I square root, it goes away, and we just call I squared -1. I cubed is the same exact thing as I squared times I. So it's 3 i's being multiplied together. Well, I know that I squared is -1, and I is just I, so we call I cubed -I. I to the fourth. I to the fourth is the same thing as I squared times I squared, which is -1 times -1. We call that 1. I'm going to put a line here, and you'll see why I put that line in just a second. If I continue this pattern, I to the fifth. I to the fifth is the same thing as I to the fourth times I. I to the fourth is just 1. I is just I. We call this I. I to the sixth is I to the fourth times I squared. I to the fourth is 1. I squared is -1. 1 times -1 is -1. I to the seventh is I to the fourth times I cubed. I to the fourth is 1. I cubed is -I. We call this -I. I to the eighth is I to the fourth times I to the fourth, which is 1 times 1, or 1. Continuing further, I to the ninth is the same thing as I to the fourth times I to the fourth times I. I to the fourth is 1 times 1 times I. We call that I. I to the 10th is I to the fourth times I to the fourth times I squared, which is 1 times 1 times -1, or -1. Hopefully you see what's happening here. I to the 11th is I to the fourth times I to the fourth. I'm getting down towards the end of the thing here. My handwriting is getting worse and worse as I go lower. Times I cubed, 1 times 1 times -I is -I. I to the 12th is I to the fourth times I to the fourth times I to the fourth, which is, 1 times 1 times 1, or 1. So I'm going to stop here. I could keep going into infinity, but I'll just point this out. Okay. So there's no need for me to keep on going because we already have a pattern that has emerged. And the final one. So what this pattern does is it comes in cycles of 4. I see you're typing something, Dave, so I'm going to let you type and I'll answer a question if you have it. Every fourth one it repeats. Absolutely, that's exactly what's going on. So if I can figure out, say I have I to the 57th. I don't want to sit there and figure that out, but if I can figure out where it falls in this cycle of I, then I can know very quickly what I to the 57th equals. All you have to do is divide by 4. 4 goes into 57. It really doesn't matter how many times it goes in. What matters is the remainder. Okay, so that is remainder 1. And let me pick a smaller number before I talk about that one. So we'll do I to the 13th. That would be the next one in the pattern. I to the 13th. We already know if it follows the same pattern, it should just be I. So 4 goes into 13. Into 13 3 times, and that gives us a remainder of 1. So anytime I have a remainder of 1 when I divide the exponent by 4, it will always correspond to I. So I to the 13th is just I. Let me do another example. Hang on just a second. So if I have I to the 14th, the next one in the pattern should be -1. So 4 goes into 14 3 times. Times 4 is 12, 2. So here I have a remainder of 2. Anytime I get a remainder of 2, it will always correspond to I squared. So I to the 14th is just -1. Continuing with the pattern. I to the 15th. Hello, Dot. I'm not sure who that is that has joined us, but welcome. I to the 15th. 4 goes into 15. Uh-oh, Dot left the room. All right. 4 goes into 15 3 times. 3 times 4 is 12. And I have a remainder of 3. Looking through the pattern, it'd be the next one up, so it should correspond to -I. And whenever you have a remainder of 3, it corresponds to I cubed. So I to the 15th is -I. And the last one, sorry if you hear my dogs, they're being rambunctious. They're playing right now, gnawing on each other. I to the 16th, well, 4 goes into 16 4 times. 4 times 4 is 16. You're not going to have a remainder when it's a multiple of 4, so remainder 0 always corresponds to I to the 4th. So I to the 16th is 1. All right, so going back to our I to the 57th, when we divided 57 by 4, we had a remainder of 1. So without even doing any more work, I know that I to the 57th is the same thing as I. Does that make sense, Dave? Excellent. So the one thing I would like to say at this point is that when you are doing calculations with I, you never want to leave I raised to any power besides 1. Because you can see no matter where you are in the patterns, I will never be raised to more than an understood first power, or it changes to -1 or +1. So you can't leave I raised to a power other than 1. You've got to change it back to whichever of the fundamental pieces of the cycle here, the first 4, it corresponds to. So you'll either write I, -1, -I, or 1. Sound good to you, Dave? Good. Let's move on. Okay, adding and subtracting complex numbers. The good news is as long as you can add and subtract polynomials, you can add and subtract complex numbers. So, sorry, I just got a mouthful of cashews. I'm hungry. Okay. So say I have 7 plus 4x plus 3 plus 2x. If you were adding these binomials together, you'd add your constants, 7 and 3, and get 10, and you'd add your variable terms and get positive 6x. Because the parentheses are really not needed there because they would be distributed away with that understood 1 that sits in front of both sets of those parentheses. So just like you combine constants with constants and variable terms with variable terms, you do the same thing when you're adding and subtracting complex numbers. So here, if I have 7 plus 3i minus 2 plus I, I'm going to rewrite that so it's easier seen. 7 plus 3i minus 2 plus I. There is an understood 1 that gets distributed there. And an understood negative 1 that gets distributed. So what I really have happening is 7 plus 3i minus 2, that's a 2, minus I. I combine my constants and get 5 and my imaginates and get positive 2i, and it needs to be written in this form as real plus coefficient imaginary. So you do the same thing with complex numbers as you do with adding binomials. So this should seem really easy to you. All right, so first example here, 5 minus 2i plus 3 plus 3i. I add my constants, 5 and 3, and get 8. And I combine my imaginary units. I have negative 2i's. I add 3 of them. That leaves me with positive 1i. Did you get that, Dave? Great. Well, I'll go ahead and run through the rest of these. 2 plus 6i minus 12 minus I. Don't forget there's an imaginary negative 1, not imaginary, an understood negative 1 that gets distributed there. So I have 2 plus 6i minus 12 plus I, which leaves me with negative 10 plus 7i. Once again, got to write it in standard form. Now, this next one's a little trickier. Multiplication. So 7i is getting distributed to both of these terms. You're going to treat those i's just like you do any other variable. So 7i times 2 is 14i. And 7i times negative 9i is negative 63i squared. You can't leave I squared there because it does not have an exponent of 1. So I squared is the same exact thing we just learned on the last page. I squared is the same thing as negative 1. So 14i minus 14i minus 63 times negative 1 gives me 14i plus 63. I can't leave it there though. 63 plus 14i is my standard form answer there. Did that make sense with the multiplication, Dave? Okay, great. So this last one, we have distribution of each to each. So I'm going to go here and here, here, and here. 5 times 6 is 30. 5 times negative 7i is negative 35i. 4i times 6 is positive 24i. And 4i times negative 7i is negative 28i squared. I've got like terms I can combine here and here, and I need to change that I squared to a negative 1. So I have 30, let's see, negative 35 plus 24 is negative 11. You subtract and take the sign of the larger. And then I have minus 28 times negative 1. So I'm just going to continue to simplify. 30 minus 11i plus 28. I've got more like terms now that I can put together here and here. And my final answer in its correct form is 58 minus 11i. Sound good, Dave? Great. Moving along. Okay, so we have these things called complex conjugates. And you've already probably studied about conjugates if you took 99 or back in high school. And that is just the same A's and B's, so the same terms, A plus B times A minus B, these would be considered conjugates. They have the same terms in the same positions. The only thing that's different is the sign between them. And this actually, A plus B times A minus B, is actually a difference of squares. I won't go into that. But let me show you what happens when you multiply complex conjugates. So complex conjugates are just the same a real and imaginary unit. You can see right here, the same real and imaginary unit. One is plus, one is minus there. All right. So when I have 7 plus 2i times 7 minus 2, I'm going to write this bigger to make it easier to see, times 7 minus 2i. So these are multiplying complex conjugates. I do the same process that I do with just multiplying binomials. I do 7 times 7 and 7 times negative 2i, 2i times 7 and 2i times negative 2i. And here's what I get. 7 times 7 is 49. 7 times negative 2i is negative 14i. 2i times 7 is positive 14i. And 2i times negative 2i is negative 4i squared. Well, notice when I multiply complex conjugates, this always happens. My two middle terms will always be opposites of each other. So they will just drop away. And right now I'm left with 49 minus 4. I'm not going to write I squared because I squared is negative 1. So I've got 49 plus 4, which is 53. So let me point out what's happened. You no longer have any imaginary units in the number. You just have a real number there. That is the whole point of knowing how to multiply complex conjugates like this. Because just like with radical expressions, You cannot have a radical in the denominator. So, since I is equal to the square root of -1, you can't have I show up in the denominator either. It's a little sad face looking at the 1 over I. You can't leave I in the denominator. And the way we get rid of having that root show up in the denominator is we multiply the denominator by its complex conjugate. Because every single time you multiply a complex number by its complex conjugate, the I terms drop out, you get an I squared on the end, which turns it all into a real number. Here's an example below. I'm going to rewrite. I start out with 3 plus 4I over 2 minus 3I. Well, the I in the denominator is a problem. We call this rationalizing the denominator when we get rid of the roots from the denominator. So, if I can multiply 2 minus 3I by its complex conjugate, I know that those i's are going to go away, and I'll just be left with a real number. Let me just say this, it doesn't matter how many i's you have show up in the numerator. It's the denominator that you cannot have a root show up in. Well, I can't just go around and multiply by 2 plus 3I whenever I feel like it. The only number that I can multiply by whenever I feel like it is 1. So what I do is I multiply this expression by a clever form of 1, 2 plus 3I over 2 plus 3I. That's just 1. Anything divided by itself is 1. So I'm multiplying my purple fraction here by 1 in green there. And here's what I get. I'm going to write out what I'm going to do before I do it to avoid confusion. I have 3 plus 4I times, okay, let me get that off of there. That is multiplied by 2 plus 3I, because you multiply fractions straight across, over 2 minus 3I times 2 plus 3I. Okay, now we have a ton of distribution to do. So, I'm going to multiply 3 by 2 and 3 by 3I and come back and multiply 4I by 2 and 4I by 3I. I'm also going to multiply 2 by 2, 2 by 3I, negative 3I by 2, and negative 3I by 3I. And here's what I get when I do that. 2 times 3 is 6. 3 times 3I is positive 9I. 4I times 2 is positive 8I. And 4I times 3I is positive 12I squared. Over 2 times 2 is 4. 2 times 3I is positive 6I. Negative 3I times 2 is negative 6I. There are those opposite terms that are going to drop out. And negative 3I times positive 3I is negative 9I squared. Okay. So these two opposite terms go away. I have like terms that I can combine in the numerator. And I'm also going to point out these I squares are really negative 1 that I'm going to multiply with. There's where I am so far. I'm just going to simplify, make this a little easier on the i's. 6 plus 17I minus 12, because positive 12 times negative 1, over 4 plus 9. Simplifying further, I can combine my 6 and my negative 12 in my numerator, and that gives me negative 6 plus 17I over 13. I cannot leave it like this. This is not standard form. I've got to put it in A plus BI form. So my final expression here is -6/13 plus 17/13 I. How was that, Dave? Uh-oh, Dave's typing. Makes me sick. Did you at least follow it? Okay, good. I am sorry that it makes you sick. Okay. So these are just some practice problems here. I'm actually going to write them. I'm going to split my screen in two here. And I'll do 5 plus 4, I guess that's I, over 4 minus I. And then I have 1 minus I over I plus 1. Okay, so we're just simplifying these expressions. So first I need to decide what is the complex conjugate that I need to multiply by. Well, in my denominator I have 4 minus I, so the complex conjugate is 4 plus I. So that's what I'm going to multiply by in the numerator and the denominator, which is really just 1. So 4 plus I over 4 plus I. And here's what that looks like. Once again, I'm going to write the multiplication before I actually do it, just to avoid confusion. Pardon me. Okay, and the denominator is 4 minus I, no ma'am, times 4 plus I. All right, so I'm going to do the distribution now. And do all this distribution as well. And I get 5 times 4 is 20. 5 times I is positive 5I. 4I times 4 is positive 16I. And 4I times I is positive 4I squared. Over 4 times 4 is 16. 4 times I is positive 4I. Negative I times 4 is negative 4I. And negative I times I is negative I squared. Now to start simplifying. So the first thing I'll point out is that those drop out. My I squares are really negative 1. I'm trying to make those bold there. And I've got like terms here in the center at the top that I can combine. So here's what my next step looks like. I have 20 plus 21I, and 4 times negative 1 is negative 4. In the denominator, I have 16 plus 1. So my next step is combining my like terms in my numerator. 20 and negative 4 leave me with 16 plus 21I over 17. Once again, I can't leave it that way. 16 over 17 plus 21 over 17I. All right, moving to the next example here. I've got I plus 1 in the denominator. Remember, it's just the denominator that you have to focus on. So, I plus 1 in the denominator, which means I need to multiply by the complex conjugate I minus 1 over I minus 1. So that's really just my clever form of 1 that I'm going to multiply by. Okay. I'm going to write out the multiplication before I do it. 1 minus I times I minus 1 over 1 plus I times, I plus 1 times I minus 1. Show my distribution. Here, 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 and here. Simplify. Oops, I forgot to show my distribution on the bottom. Here and here, here and here. So, 1 times I is 1I, or just I. 1 times negative 1 is negative 1. Negative I times I is negative I squared. And negative I times negative 1 is positive I. Over I times I is I squared. I times negative 1 is negative I. 1 times I is positive I. And 1 times negative 1 is negative 1. So I'm getting rid of my opposite terms, changing my I squares to negative 1. And here. So let me point out I have negative, negative 1 there at the top. Negative, negative 1, which is positive 1. Okay? And I also have like terms here and here that I can combine. I and I give me 2I. So I have 2I, and then I have negative 1 and negative negative 1, which is negative 1 plus 1, over negative 1 minus 1. My like terms in the numerator are actually opposites, so they go away. And I have 2I over negative 2. Well, since that 2 is a factor, it divides out. 2 divided by negative, so 2 goes into 2 once, and 2 goes into negative 2 negative 1 times. So I have I divided by negative 1, which is just negative I. All of that work to get negative I out. You'll be pleased to know, Dave, that we're on slide 7 of 9. We're almost there. Good? Thank you, sir. All right. Hey, Wes. Glad to have you. Okay, so, like I said before, whenever you have negative values under the root, you have to pull off the negative square root. So what I would not do here, I would not use the rule that says the nth root of a times b is the nth root of a times the nth root of b, because this is for distinct terms that are not negative. When you have the negative, you've got to pull it off. So in other words, this would not be the square root of negative 25 times negative 4, which would give us the square root of 100, which is 10. That is not correct. I have to pull the negative out of there. I can't work with it. So this is the same thing as square root of negative 1 times the square root of 25 times the square root of negative 1 times the square root of 4. I come back. Square root of negative 1 is I. Square root of 25 is 5. Square root of negative 1 is I. Square root of 4 is 2. This is all being multiplied. So I have 5 times 2, which is 10. I times I is I squared. However, we know I squared is really negative 1. So instead of getting positive 10, I actually get negative 10 for that value. Just a refresher on roots. When you are multiplying roots, a square root b times c square root d, you multiply outside with outside, underneath with underneath. Unless it's a negative root, and you've got to get that negative out of there before you can use this right here. Also, you can only combine like radicals. Just like you can't add 3x and 7, you can't add 3 square root 2 and 7. Those are not like terms. You can, however, add 3 square root 2 with 4 square root 2. That says you have 7 square root 2s. Okay? So you can only add like radicals. And actually, you can only add like terms, and they're only like terms if they have like radicals. So just a little review of algebra there for you. Okay, so I'll apply what we know now to adding the square root of negative 27 with the square root of negative 48. The square root of negative 27 is the same thing as the square root of negative 1 times the square root of 9 times the square root of 3. Remember, whenever you're simplifying roots, you always want to break it down into perfect square factors if you're taking the square root of it. Once again, if you are rusty on how to simplify roots, it is prerequisite. Let me look real quick on my math lab and see which prerequisite material it is, or prerequisite section it is that radicals are found in. Okay, my computer's not wanting to cooperate with me right now, so I'll put it in the news feed, whichever, I will put in the news feed which prerequisite section covers radicals. And I actually have some videos online of my own that I did that I'll post. There are videos in YouTube. I'll post those as well, the ones that are on radicals. Okay, so I'm adding that to the square root of negative 1 times, okay, 48 is 16 times 3, so 16 times 3. The reason I broke this up this way is I can take the square root of negative 1 and get I. I can take the square root of 9 and get 3. My desktop just responded to me trying to get on to, trying to open up my web browser. That's sad. Square root of negative 1 is I. Square root of 16 is 4. So when I simplify this, I have 3I square root 3 plus 4I square root 3. Now I have like terms. I have 3 of these things called I square root 3, and I have 4 of these things that I'm combining with called I square root 3. That gives me 7 of these things called I square root 3. Does that make sense, gentlemen? Wes says yes. Dave says yes, but I'm sure Dave is still feeling sick, especially with all these radicals coming back into the picture. Most students feel sick when radicals show up again. Okay, so this next one, don't let this fool you. Don't fall into the trap of, yes, Dave?
Hey, Libby, I have a question now.
Sure.
The 4 that you have, where you have square root of 16, can't that be square rooted, or am I losing something?
That is an excellent question, Dave, and that is a trap that so many students fall into, and I'll show you another example that this happens with. Let me get a different color pen from any that I have on the screen here, and I'm just going to use this little center clean section here to address that. Okay, so the square root of 16 says, what can I multiply by itself to make 16? Well, that's 4. Once you take the square root of something, it's done. It comes out of the square root. It is just the number 4 because that answers the question, what did I have to multiply by itself to make 16? What students will do is, because 4 is what we call a perfect square, they want to keep taking the square root of it and get 2. That is not good. Another one that this happens with, so once you take the square root, stop. It's out. Another one that this happens with is the square root of 81. The square root of 81 is 9. It's 9, it's done, it comes out, don't take it down to 3. So I see, Dave, that you said, I see. Wes, is that good for you too? I know you've heard this spiel before from me. Okay, Wes is approving. Very good. All right, so I'm glad you brought that up, Dave, because like I said, so many students will fall into that trap. Let me just get this off the screen so nobody gets confused here. Okay. So back to the task at hand, and that is simplifying these expressions here. So I have -2 plus the square root of -3 squared. Before I do anything, I want to simplify that root and pull that negative out. So this is the same thing as, actually let me go underneath, -2 plus the square root of -1 times the square root of 3 squared. The square root of -1 is I. So here is where I am so far. -2 plus I square root 3 squared. Now, don't fall into this trap of squaring the first term and squaring the second. We have no sum of squares rule. This literally means -2 plus I square root 3 times itself, -2 plus I square root 3. If you just square the first and square the last, you're going to be missing the entire middle term there. So I'll show the distribution that I'm going to do. -2 times -2, -2 times I square root 3, I square root 3 times -2, and I square root 3 times I square root 3. That gives me -2 times -2 is 4. -2 times I square root 3 is -2 I square root 3. I square root 3 times -2 is also -2 I square root 3. And I square root 3 times I square root 3 is positive I squared square root 9. 3 times 3. So I'm going to combine my like terms. I can take the square root of 9 and get 3, and I'm going to multiply that by I squared, which is -1. I'm running out of room here. I might have to start the next one on a new page, and I'm going to have to go and look at my PDF to read it and see what it says. I'm so sorry about the quality of the type here. All right, so I have 4. I have -2I square root 3s, and I'm combining with another -2I square root 3s. That gives me -4I square root 3s. And then -1 times 3 is -3. I now have like terms here that I can combine, and I've got to write it in standard form. So my final answer is 1 minus 4i square root 3. And I know somebody is thinking, but the i's got to come last. Well, when you have a root still in the answer, this is an acceptable way to write it. And I know students love it when we have exceptions to the rule in mathematics. Just make sure hearts sing, I'm sure. All right, let me grab this PDF real quick and see what that next problem is. I can't read it at all. I'm opening my Dropbox, so give me just a minute. Okay. Let's see. Math 1111, lecture notes, and this is 2.1. And I'm going to open up a new whiteboard page so that I have room to work this problem. And that problem is negative 14 plus the square root of negative 12 over 2. I would have never guessed that. Okay, let me get a clean page. Okay, let me write that problem on here. Let's see, it was, all right, negative, oops, I didn't have my pen. Negative 14 plus the square root of negative 12 over, terrible memory, over 2. Okay. Over 2. All right, so let's start attacking this one. We got one more slide after this, and then we'll be done, gentlemen. I appreciate y'all hanging in there with me. Okay, so I'm just going to start simplifying this thing. Negative 14 plus, and by the way, this is one of those problems that you'll end up a lot of times with a quadratic equation that will have an answer that looks like this. So you need to know how to simplify these things. Okay, so break off that negative, and then I'm going to break 12 up into 4 and 3. And that's all over 2. I'm going to come back and take the roots that I can. Square root of negative 1 is I. Square root of 4 is 2. So simplifying, here's where I am. 14 plus 2i square root 3 over 2. Now, at this point, a lot of times I see students just cross through the 2 and write 1, cross through the numerator 2 and write 1, and negative 14 and write negative 7. I'm going to show you how that works. I can only divide things that are multiplied. So if I want to divide a factor of 2 out of all of these things, I've got to have a factor of 2 in the numerator that I'm dividing out. So if I factor the numerator and pull a 2 out, I'm left with negative 7 plus I square root 3 over 2. Now I can come back and divide those 2's out, and my final answer here is negative 7 plus I square root 3. How is that, fellas? Dave says great. Wes says green check. Excellent. One more page, and they're quadratic equations. So, just to remind you, a quadratic equation to be solved with a quadratic formula needs to be in the form ax squared plus bx plus c equals 0. A is always the coefficient on the x squared term, b is always the coefficient on the x term, and c is always the constant tacked on to the end. The quadratic equation is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So the first thing I want to do is first make sure that it's in standard form there, ax squared plus bx plus c equals 0, and a is already in the form I need it to be in. I'm just going to identify my a, my b, and my c. A is 1, b is -2, and c is 2. And then I just put it into the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Notice everything I plugged in, I used parentheses. Students will make the mistake of not using parentheses and they'll end up with the wrong sign. So it's very important that whenever you plug values in, you always use parentheses. So starting to simplify, 2 plus or minus the square root of 4 minus 8 over 2. That's 2 plus or minus the square root of -4 over 2, which is 2 plus or minus the square root of -1 times the square root of 4 over 2. I can take the square root of -1 and get I. Square root of 4 is 2. So I have 2 plus or minus 2i over 2. If I factor a 2 out of the numerator, I have 1 plus or minus I over 2. I divide my 2's out. My final answer is 1 plus or minus I. Now when you put it into my math lab, they'll want 2 separate answers because there is no plus minus key. So they'll give you braces and you'll do 1 plus I, comma, 1 minus I in brace. How was that? Wes says good, Dave says good. All right, so this last one, let me change colors so it doesn't run together. I need to get it into standard form. So I'm going to subtract 8x and add 7, and I'll end up with 3x squared minus 8x plus 7 equals 0. So that means A is 3, B is -8, and C is 7. X equals the opposite of B plus or minus the square root of B squared minus 4AC over 2A, which is 8 plus or minus the square root of 64 minus, 12 times 7. I'm not good at my 12 times tables. 12 times 7, 84. Okay. Minus 84 over 6. 8 plus or minus the square root of -20 over 6. This is 8 plus or minus the square root of -1 times the square root of 4 times the square root of 5 over 6. I can come back and take the square root of -1 and get I. Square root of 4 is 2. So here's where I am so far. 8 plus or minus 2i square root 5 over 6. If I factor a 2 out of the numerator, I have 4 plus or minus I square root 5 over, I'm going to factor the 6 into 2 and 3 so that I can divide that factor of 2 out. That leaves me with 4 plus or minus I square root 5 over 3. I can't leave it in that form. It's got to be in standard form, which is 4/3 plus or minus the square root of 5 over 3I. Je suis fini. We are finished, or I am finished. Except for this last slide. Dave says, yay, green check. The sickness is over. Unit 4, 2.1, 2.2, and 2.3 are going to be due Monday, March the 17th at 11:59. That quiz will open on the 13th. The next lecture is tomorrow, again at 3 o'clock. I had to do 3:30 today because I had to pick my friend up from her chemotherapy treatment. But I'll be back at 3 o'clock tomorrow, and I'll cover section 2.2 then. 2.2 gets into graphing polynomials. So fun, fun, fun. If you gentlemen don't have any other questions, I appreciate your time this afternoon, and I hope you have a wonderful evening. You're welcome, Dave. Have a good evening. Wes, I love your smiley face. Have a good evening. I'll see ya.